Okay, cool. Okay, we're nearing the end of the course. I think we have about 6 or so lectures left. I haven't counted them, but now we're really getting into many different processing paradigms in digital design and computer architecture. And today we're going to cover 3 of them that have had significant influence on systems: VLIW, systolic arrays, and decoupled access and execute. So hopefully it's going to be a lot of fun. And a lot of principles also. A lot of principles go into building these systems, and they target different kind of applications, let's say, and hopefully it'll be clear. Next week, we're going to cover SIMD processors and GPUs, another paradigm that has had a lot of impact, of course, as you probably know well, but we'll go into how they work also, and we'll compare and contrast them to systolic arrays as well as VLIW. But let's start with VLIW, and this is the outline of the next few lectures, this week and next week, basically. And VLIW stands for Very Long Instruction Word Architectures. And this is an instruction set architecture paradigm. And you will see the philosophy of it. The philosophy is basically keep the hardware as simple as possible, and software does the hard work to extract parallelism, basically. So essentially, we've seen the multiple instruction fetch concept before. And that's the idea of superscalar processing, right? In superscalar processing, hardware fetches multiple instructions, and it's the hardware task to check dependencies between them. Compiler can help, as we discussed. Compiler can schedule instructions such that the concurrently fetched instructions don't have dependencies between them, but it doesn't have to. The superscalar processor provides a support for dependency checking for sure. VLIW has a different principle. It's very long instruction word. We will see why that is. And basically, the idea is to have the software pack independent instructions, completely independent instructions, in a larger instruction bundle to be fetched, decoded, renamed. Well, let's not talk about renaming right now. Fetched, decoded, executed, and finished concurrently. Essentially, this instruction bundle that consists of multiple small instructions flows through the pipeline at the same time. And it's the compiler's job to guarantee that they're completely independent so that the hardware doesn't need to do any dependence checking. Basically, hardware fetches and executes the instructions in the bundle concurrently. It doesn't need to do dependence checking between those concurrently fetched instructions in the VLIW model. So that's the difference between VLIW and superscalar. And after learning superscalar, VLIW is not a huge step in a conceptual manner, of course, but the thinking is very different. And because the principle is that software needs to do all the dependence checking and ensuring that the instructions can be concurrently executed, now the software needs to be very intelligent. Okay, so this is a pictorial view of the VLIW concept. You have a program counter. And with that program counter, it's still a sequential model, right? But it's not von Neumann in the sense that when you fetch the program counter, when you actually get to the program counter, you fetch multiple instructions that are concurrently executed, that can be concurrently executed without the hardware checking for dependency. So this example, you have an add, you have load, you have move, you have multiply, and they can be concurrently executed at the same time. So this is clearly based on the von Neumann model, but you're not doing one instruction at a time. You're doing multiple operations at a time. And it was introduced in the seminal paper by Josh Fisher, who introduced this enormously long word instruction computer, ELI 512. And in that computer, basically, they had 512-bit instruction words, and they could pack many instructions into those 512-bit instruction words. You can imagine, you can compare that to existing instruction words that we have in MIPS, for example. MIPS has 32 bits, right? So you can pack, assuming each instruction is 32 bits, you can pack 16 instructions to be executed concurrently. And later we will see VLIW machines that are built that can fetch, decode, execute 28 instructions concurrently. Now, of course, the compiler needs to ensure that you have 28 instructions that can be executed concurrently in a single cycle. So conceptually, it's beautiful, as you can see. So as I said, a very long instruction word consists of multiple independent instructions packed together by the compiler or the programmer. But programmer is tough, actually. In fact, the VLIW proponents also say it's very tough to program these machines. So you really need automatic compilation into them. But again, you can imagine programming at an assembly level as well. And packed instructions can be completely logically unrelated, as we have seen in the previous picture, basically. If you go back to the previous picture, add, load, move, multiply, they're different instructions, right? They're different operations. You can have floating point operations also, etc. We will see in the next lecture SIMD and vector processors, which are different. They can also do concurrent operations, but it has to be exactly the same operation. So I will show you this VLIW slide in the next week as well to contrast it with the SIMD vector processing concept. So hold on to that. So in that sense, VLIW can exploit irregular parallelism. The instructions have nothing to do with each other, so you can actually exploit fine-grained irregular parallelism between different instructions, whereas SIMD and vector processors, as we will see, cannot, because they have to exploit the parallelism where the same instruction, same operation is done on many different data elements. Okay, so I've already given you the idea, but let me repeat it again. Compiler finds independent instructions and statically schedules, in other words, packs or bundles them into a single VLIW instruction. And all of these wording, different types of wording is used in VLIW literature, packing, bundling, etc. That means putting together multiple instructions. Multiple independent instructions. So the traditional characteristics of VLIW is clearly you can fetch multiple instructions, execute multiple instructions. You have to have multiple functional units to be able to concurrently execute these instructions. One other characteristic is all instructions in a bundle are executed in lockstep. And this is because compiler controls the execution. If one instruction gets delayed for whatever reason, maybe because of a dependency, all of the instructions wait until they can move to the next stage in the pipeline. And this is a traditional characteristic of VLIW that has made its performance a little bit lower than other architectures. If you cannot get rid of the dependencies between instructions that are executed in different cycles, of course, right? And we already discussed that. That's not an easy task. And instructions in a bundle are statically aligned to be directly fed into the functional units. What does this mean? Basically, the compiler has a view of what functional units are there in the microarchitecture. And it knows exactly which functional units are in which location. So it aligns the instructions such that the instructions go directly into the functional units. So let me go back to this picture over here. These are processing elements, essentially functional units, right? Basically, the compiler knows that the adder is here, and the compiler schedules the add instruction such that it is fetched directly and routed directly to the adder, so that the hardware doesn't need to have a network or some wires to move the adder from this location to this possible location. The compiler knows that the memory pipeline is over here, so it puts the load over here. The compiler knows that the multiplier is over here, so it puts the multiply over here. Basically, the compiler needs to have, in the traditional VLIW, the compiler needs to have a very good view of what the hardware looks like, where exactly each processing element is, such that it packs the instructions in a nice way, such that the hardware doesn't need to route the instruction to the correct processing element that can execute it. This is another example of the philosophy, which we will get to. Basically, hardware stays as simple as possible. It doesn't even provide the network or the connectivity to take this instruction to this adder over here. In contrast, basically, the compiler knows the microarchitecture of the functional units and where they are, and it basically ensures that there's no need for routing. The hardware doesn't need to do any routing of this instruction to some other functional unit, because the compiler ensures that the instruction is aligned with where the functional unit is. So you can see the philosophy, hopefully. Hardware is simple, compiler complex. So let's take a look at the example execution of the VLIW performance. Here, actually, I had shown you the in-order superscalar before. I'm not showing you again. But here, basically, we're bundling 2 instructions at a time. These are 2 wide bundles. An ideal IPC should be 2, assuming compiler can pack independent instructions over here and there are no other stalls. And in this case, we achieve that ideal IPC because compiler has packed independent instructions into each slots, and there are no bubble causing dependencies between different stages in this particular case. Okay, so we get an actual IPC of 2. So life is beautiful, of course, in this case, assuming the compiler can pack instructions nicely like this. Okay, so let's talk a little bit about lockstep execution. Lockstep means all or none, also all or nothing. Basically, if any operation in a VLIW instruction stalls, all concurrent operations need to stall. And again, this is based on the VLIW philosophy. We don't want to complicate the machine. We want to have this bundle of instructions, and we're going to treat them as a bundle. We cannot really break them into pieces. The machine treats them as a bundle. The compiler scheduled them nicely as a bundle. So they just flow through the machine without breaking them into pieces. That's the idea. That's why this is lockstep. And this, of course, leads to performance issues if you have a load instruction that takes 100 cycles in a bundle, whereas all of the other instructions are adds, let's say, that are 1 cycle. Then all of the other adds, independent adds, need to wait for 99 more cycles, right? So that's not good, clearly. So people have tried to develop mechanisms, compilation mechanisms, to minimize the cost of this, which I'm not going to get into, but I'm going to point you to some lectures that may actually talk about this. Okay, I think something wrong happened with the live stream. I don't know. Can you check that? Maybe I pressed some wrong button over here while trying to look at the chat. Okay, somebody's asking, is lockstep execution related to atomic operations? No, not necessarily. Atomic operations are also all or none. That is true. But in this case, the lockstep execution is really across instructions that are independent of each other, that don't have to be executed atomically. Okay, it's really just the philosophy of the design of the machine. But yes, if you, for example, want to try to do atomic execution across all of those instructions at the same time, it's going to be easier in a VLIW machine for sure. So VLIW machine doesn't guarantee that, for example, the memory updates are done atomically by these instructions that are executed in the same bundle. So in that sense, it's not guaranteeing that sort of atomicity, but it's really doing lockstep. Okay, so in a truly VLIW machine, purely VLIW machine, the compiler handles all dependency-related stalls. And hardware does not perform any dependency checking. This actually includes dependency checking between pipeline stages as well. Not just within a pipeline stage, but also between pipeline stages. So the philosophy is actually very similar to simple reduced instruction set computers, right? Simple instructions. Hardware is simple, compiler is complex. But of course, life is not as beautiful. You run into variable latency operations like memory stalls. If a load misses in the cache, what do? So you have to have some sort of interlocking in that case, basically. You cannot get rid of all possible hardware dependency related interlocking issues, because there are some cases where things are completely dynamic, right? The compiler doesn't know essentially whether you will get a cache miss. So it cannot perfectly schedule these instructions. As a result, you have to have some stalling mechanisms that are implemented in hardware, as we discussed. And whenever you do stalling, all of the remaining instructions need to stall in the pipeline. Okay, so this is, let me talk about the VLIW process, philosophy and principles. This is one of the papers that are written by the person who has introduced VLIW, Josh Fisher. And you can see the philosophy in the title over here, right? Basically, we want to achieve parallel processing with a dumb machine, dumb meaning as simple as possible hardware, but the compiler needs to be smart. And you can see that the claim over here is that we've developed a new fine-grained parallel architecture and a compiler that together offer order of magnitude speedups for ordinary scientific code. So you can see ordinary scientific code here. In scientific code, that's very easily analyzable, where you don't have hard to predict dependencies. These machines can actually do reasonably well. And in such code where you don't have really hard to predict dependencies, you can actually do well, where the compiler can actually schedule the code really well. Where you have large blocks of code, you need to execute lots of arithmetic operations and not that many memory accesses. You can do reasonably well using VLIW machines. But let me talk a little bit more about the philosophy. So as I said earlier, philosophy is similar to RISC. Essentially, we want to have simple instructions and hardware. And RISC and VLIW were developed in the 1970s and 80s. Originally, RISC was introduced in IBM by John Koch in the 1970s, later picked up by Patterson and Hennessy at Stanford and Berkeley, where they introduced the MIPS and SPARC architectures. But IBM 801 minicomputer was the first example of a RISC machine. So what does RISC mean? Basically, we want to have simple hardware, and the compiler needs to do the scheduled code, but we have single instruction at a time. Whereas VLIW is really multiple instructions in parallel, and the compiler needs to get parallelism across multiple instructions in a clock cycle. So that's the big difference basically between RISC and VLIW. We have multiple instructions fetched in parallel. So VLIW is in a sense a bit more ambitious because you really need to get the parallelism across these fine-grained instructions. So in RISC, the compiler does the hard work to translate high-level language to simple instructions like the MIPS instructions. Even simpler. MIPS started out actually to be much simpler. Multiply wasn't there, for example. Byte-level loads were not there, etc. And initially, John Koch actually had the vision that the compiler does does not even compile to instructions. It compiles directly into the control signals. Remember, we saw the control signals in our microarchitectures. Imagine writing a compiler that compiles and orchestrates all of those control signals without even having instructions, right? You could imagine that. You could potentially think about that as an FPGA today, actually. An FPGA somewhat does that, right? If you have a compiler that compiles code into an FPGA in some manner, then you may need to manipulate some control signals if you don't have a higher level abstraction. And that was the philosophy of RISC initially when it was developed. Of course, control signals turned out to be very, very hard to compile into. So people developed the interface of having simple instructions, but as simple as possible instructions. Not complicated instructions like string copy, for example. That's too complicated. You want to add and not XOR, simple arithmetic and bitwise instructions, not even multiply, as I said. And of course, the compiler needs to reorder simple instructions for high performance to do this. And the philosophy is that hardware does little. It does little translation and decoding. It stays very simple, no dependency checking as much as possible, and no reordering of instructions. But as we discussed early, this is not an easy task to do. So if this is not an easy task to do, VLIW is even harder. So basically, the compiler does the hard work to find instruction level parallelism in VLIW across the same cycle. Within the same cycle, when you fetch multiple instructions, you need to make sure that they're parallel. And hardware stays as simple and streamlined as possible. Execute each instruction a bundle in lockstep, and compile also schedules the instructions within the pipeline so that hardware doesn't need to do dependence checking. So the reason why people wanted the hardware to stay simple is because they can now make the hardware higher frequency and easier to design. That was the thinking. But of course, this put a lot of complexity into the compilation and software frameworks. And as a result, there was a lot of activity that happened in compilation and software frameworks, as we will discuss. And that was the biggest benefit of the RISC and VLIW movement, if you will, philosophy and principles. They enabled a lot of research into compilers, and modern compilers got affected significantly because of this. So this is directly from the paper that I mentioned. Very quickly, this defines VLIW architectures. There's one central control unit issuing a single long instruction per cycle. Each long instruction consists of many tightly coupled independent operations. This is fine-grained independent operations that are independent of each other. Each operation requires a small, statically predictable number of cycles to execute. That's important. Statically predictable, so that the compiler can do the scheduling nicely. And operations can be pipelined, as you can see. And these properties distinguish VLIWs from multiprocessors, because multiprocessors parallelize code with large tasks, right? Large threads, let's say. And data flow machines don't have a single flow of control, and they don't have the tight coupling between instructions, as we have discussed also. And as we will see in the next lecture, VLIWs require none of the required regularity of a vector processor or an array processor, which we will discuss in the next lecture. And commercially, VLIW machines have been quite interesting. Josh Fisher, after he worked on VLIW at Yale University, he formed a company called Multiflow. And he and his team actually worked on very interesting processors. You can see 7-wide, 28-wide processors and compilers, I should say. A lot of work went into the compiler, of course, Multiflow trace compiler. And basically, they did build these machines, and they were successful in a small fraction of code where you could actually extract this sort of parallelism through the compiler, but they were not generally successful. Concurrently, Bob Rao with the Sidrome startup, they did the same thing. And unfortunately, again, they were not successful. These startups don't exist today. They were successful for a very small fraction of the, let's say, bigger software domain, where you don't have, where the compiler cannot easily extract this sort of parallelism. So in the end, if you cannot extract parallelism, if you cannot get 28 instructions that are completely independent in a cycle, what do? Well, you know the answer, you insert no ops, right? But once you insert no ops, you're wasting all of that parallelism, right? And that's going to be one of the problems with VLIW, as we discussed. Okay, Transmeta Crusoe, which we will very briefly discuss at the end of this particular part of the lecture, what they tried to do is they basically had a binary compilation system. They translated x86 code. They took the x86 code as a software. They binary translated into an internal VLIW engine. And they were quite power efficient. They never matched the performance of an x86 processor, but power efficiency was quite good. But again, they couldn't beat the competition from the big x86 vendors. So where VLIW has been extremely successful so far has been the digital signal processing and embedded processor market. and initially some ATI and AMD GPUs, but I think even ATI and AMD GPUs actually moved from the VLIW architecture internally in their GPU cores. But embedded systems still have VLIW, and most embedded systems actually still employ VLIW. And one of the reasons is here the code is relatively simple and relatively easy to compile into and relatively easy to disambiguate. And there are multiple reasons for this. One reason why people write that kind of code is they want code to be statically predictable also for other reasons. In an embedded system, you want to have the predictability properties of code so that you can guarantee deadlines, for example. And that property works nicely with a VLIW machine's requirement that latencies should be statically predictable also. As a result, a lot of embedded systems successfully employed VLIW. And if you actually program some of these machines, you will have to program in VLIW. But compilers also, of course, do the job as well. Okay, somehow I moved there. So a big move in terms of the general purpose microprocessor market to go into VLIW was made by Intel when they wanted to transition the x86 ISA from 32 bits to 64 bits. They said, why don't we re-examine the ISA completely? And they basically said, develop the IA64 architecture. They didn't just change the x86 to 64 bits. They basically completely revamped the instruction set architecture. And this is based on VLIW principles, but it's not fully VLIW. It didn't try to basically try to avoid some of the big issues with VLIW, like too many no-ops, etc. They called it explicitly parallel instruction computing. And the basic idea, there are multiple differences, of course, from VLIW, but what they introduced was instruction bundles can have dependent instructions now. So if you think about a pure VLIW perspective, it's a big no-no, right? I cannot have dependent instruction in my bundle. Because if you put dependent instruction in your bundle, now hardware needs to check. Now, to make hardware's job easier, they basically change the instruction format such that a few bits in the instruction format specify explicitly which instructions in the bundle are dependent on which other ones. So this is actually a cool thing. Basically, they encode the dependencies between instructions explicitly so that the hardware's job is a little bit easier. So of course, this is not a great world, if you will. There are multiple reasons why IA64 was not successful. This is also called Itanium, by the way. It's Itanium architecture. But it's not the best of both worlds, because now hardware needs to do dependency checking, of course, directed by the compiler a little bit. But software also needs to do dependency checking. So everybody is doing work right now, both software and the hardware, compiler and the microarchitecture. But the reason they introduced these dependencies inside otherwise what should have been an independent instruction bundle is because the compilers are not good at finding, let's say, 6 instructions or 8 instructions that are completely independent of each other. Sometimes not even 2 instructions, right? It depends on the code. And much of the code does not yield itself to finding that much parallelism. And whenever you cannot find that much parallelism, your instructions are dependent on each other, or you have to put no-ops like the traditional VLIW. So I would recommend taking a look at the IA64 architecture. If we have time, we will talk about it. They also introduced predicated execution, which helps VLIW as well by having long code portions, by converting control dependencies into data dependencies, which we discussed briefly last time. So there were a lot of innovative ideas. But unfortunately, one of the reasons why it was not successful is because it changed too much in the software stack. So everybody needs to recompile their code to get the 64-bit benefits. Concurrently, what AMD did at the time was they developed the x86-64 architecture, essentially. They basically said, we're just going to extend the x86 architecture so that it's 64 bits. We're not going to change anything else. And as a result, their solution to extend the x86 architecture to 64 bits was adopted much more easily by essentially everything in the software stack. And IA64 was not adopted, and it had a lot of difficulties. And I'm not sure if Intel is really producing these machines anymore, maybe for a very small fraction of the market. So there are some questions over here. Let me see. Are the instructions also committed concurrently? Yes. The answer is yes. Basically, they flow through the entire pipeline concurrently. So the AMD K5 was a VLIW machine? No. AMD K5 was a superscalar machine, basically, and an out-of-order machine, actually, after that. And then are VLIW machines possibly useful for machine learning applications? Well, let's wait on that. Basically, any machine can be useful for machine learning applications, right? And there's a question, how is error handling done if instructions are committed concurrently? Well, basically, you need to check the errors on a per instruction basis. And if you cannot commit the entire instruction, yes, you may need to break it at that point. So that's a very good point, actually. if the instructions are completely committed at the same time, if the instructions are committed concurrently, if there are no exceptions. But if there are exceptions, you need to handle them in a manner. And VLIW architecture specifies exception handling also. So you need to look at the ISA manual in terms of how the exceptions should be handled and interrupts should be handled in a VLIW machine. So that's a very good question. Okay, so let's talk about the advantages and disadvantages of the VLIW trade-offs. Basically, the key advantage is there's no need for dynamic scheduling hardware. So out-of-order execution is not needed, assuming this works, of course. So you get simple hardware. And superscalar execution is not needed. Again, dependency checking is not needed. So no need for dependency checking within a VLIW instruction, simple hardware for multiple instruction issue. And there's no need for renaming because compiler handles all of that, hopefully. No need for instruction alignment and distribution after fetch to different functional units. Again, hardware stays simple. You can see that advantages are all simple hardware, right? As expected, right? Because that's the philosophy and that's the principle. But of course, this leads to a big disadvantage. Now compiler needs to, or the programmer needs to find n independent operations per cycle. And if it cannot, they insert no ops in a VLIW instruction. And you already know the big downsides of no ops, right? They basically, you lose parallelism. Your machine is 28 wide. You're executing 2 instructions because you cannot find parallelism that is 28 instructions wide, let's say. This leads to parallelism loss. It also leads to code size increase because no ops need to be encoded somehow in your instruction set architecture. But the VLIW folks actually did, wait a second, something interesting happened here. I guess I have to sign in again. Sorry about that. Somehow Zoom is asking me to leave the meeting. I don't know why. Let me see. This is interesting. Okay. Yeah. Let me see. I guess Zoom logged me out somehow, so I need to log in again. Let's do this. How do we log in again? Okay. Let's do it. Okay. It was asking me to leave the meeting for some reason. I don't know. I guess we need to be signed in. Yes, but interesting. Okay. I think I'm signed in again. Okay. Can you still see the slides? Okay, good. Okay, cool. Good. At least we didn't have to end the lecture and restart it. That would have been a pain. But now we can continue. Okay. Basically, you get parallelism loss and code size increase. But code size increase happens if you have to actually encode the no-ops, right, in your instruction stream. So VLIW researchers figured out a nice way of encoding no-ops such that they don't take space. So for example, you could indicate that there will be 5 no-ops after this instruction. They came up with a really cool, let's say cute instruction encoding such that they could encode any number of no-ops without taking 32 bits per no-op. You can see the problems that VLIW causes in terms of encoding, right? You'll have to encode no-ops. So code size increase is less of a problem, but parallelism loss is still there. Okay, so there are also other disadvantages. Whenever you change the execution width, instruction latencies, functional units, basically anything in your microarchitecture that affects instruction scheduling, you have to recompile code. And this is a downside. For example, going from a 7-wide VLIW to 28-wide VLIW, you need to recompile code. And there's no way around it, basically. And this is a big problem, right? Whenever you do superscalar out-of-order processing, if you have something you change in the microarchitecture, you don't need to recompile code, right? Okay. And lockstep execution causes independent operations to stall because no instruction can progress until the longest latency instruction completes. And as we discussed, that's a problem also. The compiler can try to schedule around it such that it tries to balance the execution latencies of different instructions that are executing at the same time concurrently. But again, that's a difficult task. That's asking even more from the compiler now. Okay, so let me summarize VLIW. We're almost done. I'm just going to give you some papers to potentially read. But basically, VLIW is actually a quite cool and powerful concept that has impacted microarchitectures, especially the compilers that we built today. It simplifies hardware, but requires complex compiler techniques. So solely compiler approach of VLIW has several downsides that reduce performance. You get too many no-ops. not enough parallelism is discovered. Even after employing many, many interesting compiler techniques that we will briefly talk about, static schedule is intimately tied to the microarchitecture. Now, code optimized for one generation performs poorly next. That's bad, basically. You have to recompile every single time. It may not even execute for the next generation. You should think about that also. And there's no tolerance for variable or long latency operations because of this lockstep nature. So it doesn't have the beauty of data flow or out-of-order execution in basically executing instructions in parallel while you're waiting for some other instructions, right? So these are the downsides, but there are two big upsides, basically. And the big upsides are most compiler optimizations developed for VLIW are actually employed in optimizing compilers today. So no op means no operation, right? We've seen this before, just to make sure it's clear to everyone. But basically, if you look at an optimizing compiler today, they basically use a lot of the concepts that are developed for VLIW compilation, because superscalar machines can benefit from that as well. So they have enabled code optimizations. These compilation mechanisms have enabled a lot of code optimizations as well. I'm not going to go into the details since that's not the subject of this course, but I would recommend you take a look at some of the lectures. And if you're interested, take a backend compilers course that discusses these issues. And also VLIW has been very successful when parallelism is easier to find by the compiler. And this has been true in traditionally embedded markets, DSPs, and in early forms of GPUs where your target was really graphics. Today's GPUs have evolved into more general purpose engines. So graphics is a domain where you have a lot of parallelism, right? You're processing an image, for example, or a video. It's highly parallel, clearly, and you can do VLIW on it relatively easily. But if you're doing general purpose computation on a GPU, now maybe VLIW doesn't make sense. As a result, some companies that used to use VLIW in their internal shader cores, for example, in their GPUs, they had to move to some other techniques that are less VLIW, let's say. We'll talk about GPUs in the next lecture. Okay, so that's a big summary. So one example, I'll give you some example works, is trace scheduling. This was actually developed earlier than this VLIW paper. The idea of trace scheduling is really to find frequently executed parts of the code. So you have this complex control flow graph with instructions inside each block over here. And these are basically control flow. Basically, you profile the code to figure out frequently executed blocks. That's what you do over here. You combine them into a single basic block, take out the dependencies over here. And then if this code is executed like this, if this is actually your executed path, you basically optimize the code very nicely across that path. If this is not, then you have to figure out what to do. And these are called fix-up code, as you can see over here. You have to add a little more code if the machine actually doesn't execute this path at runtime. So compiler can profile the code to figure out the frequently executed paths, such that it can compile mainly to it. But if for this to work well, the frequently executed path actually has to be the path that is actually executed at runtime also. So this is the idea of trace scheduling. It's a very powerful idea employed in modern compilers. Later ideas actually superseded trace scheduling, as we will see. And I would recommend this paper that I mentioned earlier. This is a very long instruction word architectures and the ELI 512 paper. And actually, at Yale, John Ellis, a PhD student of Josh Fisher, developed a Bulldog VLIW compiler, which precedes a lot of the analyses that are done in modern compilers. You can see there are flow analyses. They even do memory bank disambiguation, because you need to make sure that the instructions that you schedule together don't conflict in a memory bank. We will see that later on, actually, in the next week's lectures. This is a problem with SIMD architectures also, but this is a problem when you have statically scheduled code also. You need to make sure the instructions flow in the machine, in all parts of the machine, without actually conflicting with each other anywhere. Remember, we talked about memory banks at the mysteries lectures. We have the same problem in a VLIW architecture. If you have multiple instructions concurrently executing, they'd better go to different banks and they don't conflict with each other in the row buffers of a single bank. And the compiler needs to try to figure this out as early as 1980s, as you can see. And this is a very tough task, actually. This is one of the contributions of this work, but this is a very, 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 very tough task in a machine and a compiler also. And you can see there's trace scheduler, code generator, etc. I'm not going to talk about that. There's also memory disambiguation that you need to do, whether two references go to the same location whenever you have pointer accesses, for example. And that's one of the big problems in compilation, how to disambiguate these dependencies. Okay, another example is a superblock technique, which I'm not going to go into, and you can take a look at that. You can see that this was proposed for both VLIW and superscalar compilation. It was developed to improve over trace scheduling. And there was a lot of work done by Wenmei Hu's group at Illinois to actually provide a compilation framework for multiple instruction issue processors, both superscalar and VLIW. This was highly influenced by the work that I showed you earlier from Josh Fisher. And this is another example of that work. Many of these works actually have won test of time awards because they've influenced modern compilers. This one is one example. Superblock is another example, actually. And if you're interested in static scheduling more, I would definitely recommend that you take a look at our lectures on static scheduling, because this is actually a lot of fun, in my opinion. And there's a more compact version that covers both branch prediction and static scheduling in a shorter way. Okay, let me give you one aside and we will conclude VLIW. And I give this aside because we talked about ISA translation before, but I'm going to talk about why Transmeta translated the x86 ISA to VLIW. Basically, we said earlier that one can translate from one ISA to another internal ISA to get to a better trade-off space. Your programmer visible ISA may not be great, x86, let's say, but you can make your implementation ISA really cool and easy to design hardware for, right? And in between, you employ some translation mechanism. So complex instructions, for example, can be mapped to simple instructions. Internally, x86 architectures today do it, microarchitectures. Or scalar ISA can be mapped to a VLIW ISA internally. So there are multiple examples of this. Intel's and AMD's x86 processor implementations today translate x86 instructions into programmer invisible microoperations or simple instructions in hardware. So that's hardware-based translation. And Transmeta's x86 implementation, which used to exist a while ago, are translated, basically they translated x86 instructions into secret VLIW instructions in software. They call this the code morphing software. And it's actually very interesting, and there are many trade-offs associated with this translation I'm not going to go into. But this is an example picture from the Transmeta's white paper, which is actually a nice white paper that talks about a lot of technical issues. If you can find it online, I would recommend taking a look at it. But basically, they translated using this code morphing software, it's a binary translator, x86 instructions to VLIW instructions. And there are multiple reasons why they did it, because clearly they wanted to execute x86 because that's where the biggest code base was at least in late 1990s. And while they were trying to binary translate into their engine, they needed to do a lot of code scheduling also. And VLIW was a very good target for them because VLIW simplifies their hardware that enables them to build very nice hardware and also at the same time take advantage of the binary translation mechanism to do code scheduling. Essentially, what they have is a just-in-time compiler that compiles x86 code into an internal VLIW processor. And in the end, they gained a lot on power efficiency, but they didn't, as far as I know, they weren't able to match the performance of the x86 processors of the day. And as a result, you probably don't hear about Transmeta as a company that exists today. Okay, there's a lot more to cover on ISAs as well, and I'd recommend you to take a look at these lectures. I've already done this, so I'm going to skip these. So that brings us to the end of 19A VLIW. Okay, now that we've learned about VLIW, let's move on to the next big idea, systolic arrays. This is an idea that was actually developed around the same time, and it has had a lot of impact similar to VLIW. And as you will see, it actually forms the core of many machine learning accelerators today due to its specialized nature to do matrix multiplication, and in particular convolutions, which is at the core of many convolutional neural networks today. And I like this idea a lot, actually. I used to teach it much earlier than it became popular with the machine learning accelerators, because fundamentally it's a good idea to design an accelerator. And I think it's always good to think about these good ideas because they may find their matching applications at some point into the future, especially when they provide some fundamental benefits like what we will see today. Okay, before I jump into systolic arrays, I will just, since some registrations are going on right now, if you're interested in learning more about computer architecture, we offer a seminar in computer architecture every semester, actually, not just fall. Right now, the seminar is happening, for example. You can take a look at the seminar course at this link over here. And it's essentially a rigorous seminar on fundamental and cutting-edge topics in computer architecture. You get to learn how to do critical presentations, reviews, and discussions of seminal works in computer architecture. Some of them are cutting edge, some of them are seminal. And it's going to be interesting if you take it. A lot of students actually like it, I think. It's a bit work, but you get a lot of benefits, in my opinion, from the work that you do. And we cover many issues and ideas and perform, especially the important part for me is critical thinking and discussion. So you can register for the course online if you're interested. And some of the current courses are also live streamed or uploaded. So you can take a look at the format if you're interested. And if you're in general interested in learning more and doing research in computer architecture, I have 3 suggestions. Feel free to email me with your interest, CC Juan and any other TA you may work with, and we'll be happy to talk. I would suggest taking the seminar course and the computer architecture course, which is a more advanced course. And if you're doing the readings and extra assignments on your own, especially the readings that I specified, none of the readings are required, as you know, but some of the readings are even less required than others, as you probably have guessed. But those probably show your interest in computer architecture. So feel free to contact us, because this is a really great time in computer architecture. Some people call it the golden age of computer architecture, because everything is bottlenecked by computer architecture today, as we will see in this lecture also. And there are many exciting projects and research topics on a lot of these topics that I list over here. I'm not going to talk more about this, but there's a limited list on our group's website. And this is a limited list because it doesn't cover everything, because there's just not enough time to write up about everything we are working on. So you can contact us. Okay, so with that announcement, let's continue with the other execution paradigms to get higher level concurrency in our systems. And systolic arrays is going to be the next one. And hopefully we will have time to cover in a short way decoupled access and execute, because it's a relatively small idea to cover. It's an important idea though. So these are some readings that I would recommend you to do. I'm going to cover Why Systolic Architectures paper by H.T. Kung, which is a beautiful seminal paper. And we're going to cover, there's a more recent systolic array paper that talks about Google's tensor processing unit, which is at the core of systolic array architecture. If you remember from lecture 1, I mentioned this to you, and I mentioned that you're going to learn about it in lecture 19 or so, and today is lecture 19. So we're going to talk about Google's TPU as well, which is based on the systolic array principles. And next week, we're going to talk about GPUs. And this is these are both recommended readings overall, and an earlier version of the impact of single instruction, multiple data architectures in instruction set, in the x86 instruction set architecture, the multimedia extensions. So it's going to be fun. We're going to talk about both single instruction, multiple data, and GPUs. But let's jump into systolic arrays. So basically, what was the motivation for designing what's called a systolic array? Essentially, people wanted to design an accelerator that has a simple, regular design, similar to what we have discussed earlier, VLIW, right? We want the hardware to be simple, regular, and we want to replicate it. So we want to keep the unique parts small, number of unique parts small and regular. We want high concurrency, clearly. We want high performance. And especially at that time, these accelerators were being thought of for tasks like linear algebra, vision, image processing, similarly to the neural networks of today, right? So basically, we wanted high concurrency at the time. And most importantly, in the design of an accelerator, you needed to balance the computation and I/O and memory bandwidth. This will become more clear in a little bit. Basically, you want to maximize the number of operations you do on an element that you fetch from memory, because memory fetch is expensive. You don't want to go back to memory many, many times like a CPU does. Basically, whenever you fetch a single data element, you want to transform it inside the machine between processing elements so that you don't need to fetch it and write it back to memory, fetch it, write it back to memory, fetch it, write it back to memory many, many times. That's the idea over here. And the idea is to basically to achieve all of these 3 goals. The idea is to replace a single processing element with a regular array, vector or array of processing elements, and carefully orchestrate the flow of data to this array and between the processing elements in the array. So we will see what this means more clearly, such that these processing elements collectively transform a piece of input data before outputting it to memory. You want to maximize the operations you do on the data before you have to write it back. And this maximizes the computation done on a single piece of data element brought from memory. And that's the one big benefit of a systolic array architecture. So basically, the picture looks like this at a high level. This is from the paper that I recommended to you. Essentially, instead of having a single processing element that basically keeps fetching data and writing it back to memory, you basically have, in this particular case, a string of processing elements or vector of processing elements that are connected to each other in a linear fashion. As you can see, there are six elements over here. And basically, you fetch the data, one processing element does something to it, passes it on to the another processing element. This processing element does something to it, passes it on to the next processing element, etc., etc. And you can see that the benefit over here is 30 million operations at that time, as opposed to 5 million operations, because you're basically using the data item 6 times, let's say, as opposed to going to memory 6 times for the same data item or transformed version of the data item. So that's the basic principle, to maximize the usage of a data item. And this is one example of a systolic array. You basically have 6 processing elements. But as we will see, systolic arrays can be 2-dimensional as well, or not so regular as well. They may have different diagonals as well. We will see some examples of this. So linear is, of course, the simplest example, right? And the connections can be multidimensional and not as regular as we see over here. Basically, this processing element may be back connected to this processing element also. So we will also see the differences from pipelining soon. So basically, this is inspired by actually human architecture, let's say. Essentially, memory can be thought of as the heart. It's pumping blood to the cells that are processing elements. So data is blood, and processing elements are cells. And memory pulses data through the processing elements. So if you think about our heart, we have a vein system where data or blood flows through the cells, right? And the cells really operate on that blood to do whatever they need to do, right? Cells are not individually connected to memory one by one, and we don't have a single cell. Otherwise, that would not be scalable. So the scalability really comes from pulsing of the data through the veins into the cells, such that the cells transform the data and eventually the data flows back to memory or the heart, and then it gets recirculated again, right? So that's a nice analogy, and I think this is an analogy that has been successful, and it makes sense. And if you want to learn more about the analogy, you can read this paper. So basically, the other way of phrasing this idea is data flows from the computer memory in a rhythmic fashion, passing through many processing elements before it returns to memory. So you need to orchestrate the data, and we will see what this means. So similar to blood flow, heart pumps data into many cells, and many cells return the data to the heart, and this keeps going on and on, essentially. And different cells process the blood. Many veins operate simultaneously, and this can be many dimensional also. Okay, so why? Because special purpose and accelerators and architectures need what we discussed earlier: simple and regular design, high concurrency, and very importantly, balanced computation and I/O, or memory bandwidth. So as we discussed, the basic principle is to replace a single processing element with a regular array of processing elements and carefully orchestrate the flow of data between the processing elements, as well as from the memory into the processing elements and processing elements out to the memory, to balance computation and memory bandwidth. So you may say, okay, this looks like a pipeline, right? But it's not like a pipeline. There's some similarity, but there are significant differences also. Basically, first of all, these are individual processing elements. In fact, each processing element can potentially be pipelined. I'm not going to talk about it right now, but you may see. These are individual processing elements. It could be a processor also, as we will see later, but initially these are specialized functional units. But you're really not fetching instructions. Basically, you're not dividing the instruction processing cycle between them. These are individual processing elements that may be doing exactly the same thing to the data. For example, it's just data is flowing through them, okay? Array structure can also be nonlinear and multidimensional, and clearly our pipelines were never nonlinear and multidimensional. I mean, we of course made the pipelines more complicated, but it was also always a linear flow. And processing element connections can be multidirectional and different speeds because they can communicate with each other, because it basically all stems from the fact that these are individual processing elements and they can communicate with each other, as opposed to a pipeline that's designed carefully to really break the instruction processing into multiple cycles. Processing elements can have local memory and execute kernels, basically, rather than a piece of the instruction. And we will see that. Initially, when they were proposed, it was not like that. But over time, actually, processing elements became more sophisticated to run more general purpose code, and it can have local memories inside each of these processing elements. So it's fascinating, basically, what you can build out of this. And it's lead to concepts like pipelined parallel programming, which is also different from pipelining, even though the pipeline is in the name, and a lot of interesting concepts, as we will see soon. Okay, let me give you a systolic computation example, and I will take a detour into convolutional neural networks because it's really important at this point to discuss why systolic computation has been so successful, why systolic arrays have been so successful for neural networks as well. Because I'm not giving this lecture in 2010 right now. When I first started giving this lecture, at that time, none of these convolutional neural network accelerators existed. Right now, we have them. So I will motivate it with the convolutional neural network accelerators. But convolution was one of the major reasons why systolic arrays were built. And you can find this in the H.T. Kung paper. And convolution is a very basic mathematical operation or statistical operation where you filter an input element using essentially some weights, let's say, and you will see the operation soon. Basically, it's used in adaptive filtering, pattern matching, correlation finding, polynomial evaluation, etc. Many image processing tasks, many vision processing tasks, and lately many machine learning tasks. We can have up to hundreds of convolutional layers in convolutional neural networks, as we will see, as we will discuss. So basically, what is the convolution operation? It's mathematically defined this way. Given the sequence of weights, weight 1 through weight k, and the input sequence y1 through that, basically, you can read it on your own. Convolution is the result sequence, input sequence x1 through xn. Convolution is the result sequence y1 through that, defined by this computation. W1 xi plus W2 xi plus 1 dot, 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 as you can see over here. So it's a mathematical definition. You're basically applying a filter of weights to an input sequence. I'm going to demonstrate this pictorially more in a little bit. But basically, existing convolutional neural networks do many of these convolutions on an input image. So convolutional neural networks have been developed for image recognition. For example, in this particular case, handwritten digit recognition. LeNet is a convolutional neural network that's specifically designed for handwritten digit recognition. You can see it takes an input image, and it basically uses some filtering, convolution-based filtering. This is one layer of the network to generate some feature maps on different parts of the image. And then it subsamples the image, does something else, and then it does some more convolution on top of it, and then some more sampling. And then basically it has some other layers to actually basically make sense of what this image consists of and what digit it maps to, basically. My purpose here is not to give you an introduction to neural networks. You should really take a machine learning course to really understand those topics. But essentially, the key takeaway is convolutions are used in these networks a lot, right? Okay, I see some questions, but I cannot see all of them for some reason. My chat is not working anymore very well. Okay, yeah, there's nothing I can answer at this point. I can see at least. Okay, but basically, I think the question is about perceptrons versus convolution. So convolution is a mathematical operation. Perceptron is a single layer network, I should say. It's not a neural network, but it's basically the representation of a neuron. Neural networks are multi-layers. There's also a multi-layer perceptron. But modern neural networks are, let's say, based loosely on the idea of the perceptron. Perceptron also does some weighting on inputs, right? So basically, there's some similarity, as you mentioned, over here. No question about that. But existing neural networks do much more than a perceptron because you need to transform the input using multiple layers. And also the training of the perceptron was very, very simple, as we briefly discussed last time. The training of existing neural networks is done in a much, much more sophisticated way through something called backpropagation, which is really out of the scope of this course. But basically, what I'm showing over here is how you use a trained network to do inference. So in any network, you need to train it with a sample set of images, for example, to really construct these weights and these different layers. And then whenever you're given an input, you need to do inference so that you can infer what the input should be classified as. So we're looking at inference over here. You're given an input, and actually you're trying to figure out whether the input is A, B, C, D, E, F, G, or something like that. So you need to have a trained network for that purpose. And for both, actually, for both inference and training, you need convolutions, but you use them in a different way in inference and training. So as we discussed in perceptron, you need to train the perceptron, and then you need to do inference on it or prediction on it. A multi-layer deep neural network, you still need to do the same thing, except you need to do many, many more operations for both training as well as inference. Okay, so the purpose of this picture is to show that you need to do convolutions to actually understand different parts of an image, to filter them out, to figure out what's going on internally. So it's a lot of statistical processing in the end, as you can see over here. And I'm not going to go into details because there are many networks with many different details. But at the basic level, the convolution looks like this, basically. This is one convolutional layer of a neural network. So if you go back to this, you basically are looking at this layer over here. And one convolutional layer, you take essentially some input. It could be part of an image. The blue part is an input over here. You have a filter. Input is 5 by 5, as you can see over here. Filter is 3 by 3. That's gray. Filter is going through, basically going over the input, as you can see. Output is 5 by 5, green. And in one layer of the neural network, you have the input image, or whatever input is coming from the previous layer. And you basically apply the filter, or the kernel, let's say, on top of this input, such that you do convolution operations so that you produce the output. And convolution operations were defined earlier, as we discussed, right? That's the operation. And of course, you may need to do padding, for example, because your input and output may not match exactly, or input and kernel may not match exactly. I'm not going to go into the details, but clearly, hopefully this picture shows you that you're basically applying the filter to all different parts of the input so that you can get an output feature map. Okay, that later you can subsample the output feature map, for example. So that's another example that shows basically convolution computation. I haven't verified the correctness of this convolution computation, but assuming that the convolution computation is true, this is what you get basically. Okay, so if you're interested in convolutional neural networks, Jan LeCun, who is one of the big names who have essentially been part of the machine learning revolution more recently, has a web page that talks about LeNet and talks about how it processes input images and essentially recognizes what digits are passing through. And you can see how the different layers also operate, what are the outputs of different layers internally inside the network, etc. But basically, I'm not going to go into more detail. You can learn a lot more about this topic clearly. So convolutional layers can be implemented using matrix multiplication as well. In fact, matrix multiplication, that's what you may do to map a convolution operation into a GPU, for example, or a CPU, or a systolic array. Again, this picture over here shows how you would take the convolution and implement it as a matrix multiplication. So these are the input features, these are the convolutional filters, and these are the output features. Essentially, you could consider this a convolutional layer. Basically, you construct a convolutional filter matrix, and you also construct an input feature matrix, and you basically do matrix multiplication. So this is not fully correct. We're going to put a correct version of it online, but don't worry about the numbers. But the takeaway is that you're changing the convolution computation to matrix multiplication over here so that you can map it to your hardware better, especially GPUs. And the key is basically converting the convolutional filters into a matrix and converting the input features into a matrix and multiplying them through matrix multiplication such that the result is a convolution operation as specified by the convolution. Okay, and this has been very powerful. In fact, here I would also maybe pitch in the importance of applied courses like the course you're taking and maybe other courses you may take. Essentially, applied courses are very powerful because students can actually do work and do research that can revolutionize computing. And that's essentially what happened at the University of Toronto in the early 2010s. Basically, GPUs were important at the time. GPUs were becoming very important. And there were professors who were actually teaching courses on how to program GPUs, essentially. And some of machine learning students, PhD students, these are, who are Jeff Hinton's students. Jeff Hinton is actually one of the pioneers in machine learning also, who developed some of the earliest backpropagation algorithms, for example, which got not a whole lot of attention initially. But after his students actually took this course and they implemented a deep neural network on a GPU, and they were able to train it with more than 1 million images, and they were able to win the ImageNet competition in terms of how well they can recognize the images, that backpropagation algorithm and the convolutional neural networks took off, because now with the power of a powerful GPU hardware, they were actually able to do the computations that were required to train these networks. So initially, when backpropagation was developed in the 1980s, it was too difficult to do to perform. Well, there were two major problems. First of all, there were not a lot of data. Second, it was too difficult to perform all of those computations easily in processors, but GPUs made it a lot easier actually to train a neural network with many images. And this is an example of computer architecture really enabling I don't know how to call it, maybe the second machine learning revolution, such that actually machine learning now it has become much more powerful. Basically, these are the students who were able to show through an applied course that they could do ImageNet classification. And you can read this paper. This is actually the paper that has enabled a lot of machine learning to take off recently. They were able to show that compared to the state of the art at the time, they were able to get 10% higher accuracy in classification tasks by using this deep neural network, and actually have a very efficient by having a very efficient GPU implementation of the convolution operation. You can see in the abstract of the paper, they say to make training faster, we use non-saturating neurons and a very efficient GPU implementation of the convolution operation. Now you can see the error rates. And you can see that the neural network is big actually, and even current bigger neural networks are much bigger. They basically say it has 60 million parameters and 650,000 neurons. Okay, and you can read the paper if you're interested in this. And this is a seminal paper and a recent paper that has enabled machine learning. Later on, basically, machine learning essentially took off. This is basically Google introduced the GoogleNet, where they showed that they could get even higher accuracy by adding more network layers and other optimizations. Basically, in AlexNet, in the previous version over here, there were 8 layers, and Google increased it to 22. And later, ResNet actually in 2015 or 2016 was able to reach better than human accuracy. As you can see, the human accuracy is supposed to be about 5% according to experiments. And they were able to get, this is the error rate, let's say human error rate in the image tasks that are input. And the ResNet accuracy was about 3.6%, as you can see. But first CNN made a big difference, basically. Previously, ImageNet tasks were done using some other algorithms, not machine learning algorithms. But you can see that the first CNN trained on a GPU enabled a huge increase in accuracy or reduction in misprediction rate. And later, all of the winners of the image classification task were CNNs. And the latest winner at the time was a 152-layer network. Today, we have networks that are even deeper. Okay, so this is some motivation. And if you're interested, you can certainly learn more about neural networks. But you can see that convolutions are a big part of it. There are other layers, but convolutions are actually extremely expensive in terms of computation. Okay, so now we know about convolutions, and we know about why they're important, especially today. I think they were important earlier also, but today, clearly, machine learning is a huge application that's being used by essentially everyone, inference and training. So they're even more important today. Now let's take a look at how a systolic array at a very basic level accelerates this convolution operation. And this is basically it. This is the example that I'm going to show you. This is the example that was designed. That was one of the designs that was introduced in H.T. Kung's paper. And you can see there are processing elements organized in a linear fashion. And you can see that the input data, x's, flow from left to right. And you can see there are 3 processing elements over here. And here we are computing y1 equals w1x1, w2x plus w2x2 plus w3x3. So each processing element has a weight inside it that's stationary, that stays there in a register, for example. And the processing element behaves this way. There are 2 inputs, x in and y in. Y in is going to be the output later on. But basically, what the processing element does is, there's also x out. There are 2 outputs, x out and y out. You can see that x's flow from left to right, y's flow from right to left. Weights is static. Assume that that's the case. So basically, what this processing element does is basically it sets x out to x in at the end of the cycle. At the end of the cycle, it sets y out to y in plus w times x in. So what is this? This is a multiply and accumulate, which is the basis of matrix multiplication and basis of the convolution operation as well. You need to do multiply, accumulate, right? Basically, you set y out to y in plus w, which is static, times x in. Okay, so you operate on the 2 inputs times the weight, plus the weight, and y out goes. So how does it happen? Basically, you need to orchestrate the data flow nicely. You can see that x1 is sent first, there's a bubble, and then X2 is sent, and then there's a bubble, and then X3 is sent. So basically, every other cycle, you send an input X element into this systolic array. And once X1 arrives here, you should also have Y1 arrive here. Okay, once X2 arrives here, you should also have Y2 arrive here. Okay, basically, you need to make sure that you get the data flowing from the left and the output that you're going to accumulate into that's flowing from the right come actually at the right times. That's what I mean by orchestrating the data flow. But if you look at this example, the results you will get when X1 arrives here and Y1 arrives here will be here. Here we don't get the X out because we're not going to do anything with X anymore. So basically, the result over here, this output will be W1 X1, right? I think so, yeah. So Y1 is equal to W1 X1. Okay, basically you accumulate things onto the Y1. Initially Y1 is 0. You should also assume that basically initially Y1 is provided as 0. But once Y1 goes here, X2 also arrives here. Basically Y1 also accumulates W to X2. And once Y1 goes here, X3 also comes here, and then Y1 accumulates W3 plus X3. So basically at the end, when Y1 gets output over here, you get W1 X1, W2 plus W2 X2 plus W3 X3 by just flowing the data through these processing elements that have different weights, W1, W2, W3. And you can convince yourself you could do this for Y2 by orchestrating the data in a different way, and Y3 as well. But I'm not going to do that at this point. But I'm going to show you a later matrix multiplication example that's going to be maybe even more intuitive to some of you, since you may have studied matrix multiplication. But that's basically it. We have a processing element, very simple, and we connect the processing elements such that we can flow the data nicely into them to accomplish convolution. There's nothing fancier than that, and it's very specialized, as you can see. The processing element is just doing multiply and accumulate and pass the Xn value to the outside. Okay. Okay. So you can actually improve that. If you read the paper, and I would recommend reading the paper, you can actually improve this design in many ways. There are many other designs as well. You can see that. So I think there's one question. This way, X is always the same. No. Yes, X is always the same because X is not an output, right? X is the inputs. So basically, you can think of filter is inside the processing elements. Different filter weights are inside the processing elements. X is the input. Y is the output. So X remains the same, and X should remain the same. Okay, are the weights distributed to the processing elements according to the necessary computation? Absolutely, yes. Well, you need to distribute the weights to the processing elements according to what computation you're trying to achieve. And we will see that that's going to be important. How are the weights determined and assigned? Well, that depends on what you need to do. So weights are determined. For example, if you're doing inference over here, weights are determined by the training algorithm. This may be your convolutional layer, for example. And in that layer, you know what weights to use because you've already trained your machine learning model, right? So these are all good questions, but they're more essentially, the second one is essentially, you need to determine the weights to use, of course, and that is part of your function that you need to accomplish. Okay, so if you look at the paper, what you can do is you can implement the adder and multiplier separately also and orchestrate the flow of data into those separately such that you can overlap the addition and multiplication executions. Here, we don't have that over here. So there are some disadvantages to this that I'm not going to cover. I would recommend that you take a look at the nicely written paper, but you can actually improve the performance, improve the throughput of this sort of convolutional arrays, let's say, or systolic arrays, essentially, by doing different tricks like partitioning the operations and partitioning the data flow accordingly. Okay, so basically, I think what I'm getting at, again, is one needs to carefully orchestrate when data elements are input to the array, and one needs to, of course, put the weights carefully as well, and when the output is buffered as well. So this gets more involved when array dimensionality increases and processing elements are less predictable in terms of latency. Initially, when convolutional neural networks were designed, they were not, they actually had fixed latency. But if you, for example, start adding memory accesses inside the processing elements, then you run into some issues. Usually people don't do that, but there might be some application scenarios where you may actually need to do it. But let me give you an example very quickly. This is actually going to be part of your homework, so I'm not going to solve the entire thing. But this is an example 2D systolic array computation. We're going to multiply two 3x3 matrices, as you can see, and keep the final result in processing element accumulators. So in this case, processing elements will host the result. We're going to accumulate the data inside the processing elements. And this is the basic processing element that I'm going to give you. Actually, in your homework, you're going to reverse engineer this and try to figure out how to do it. But basically, let's say this is the processing element. R is the accumulator. Inputs are N and M. Outputs are Q and P. And it's two-dimensional, as you can see, because we're going to communicate with all of our neighbors, as you can see. Basically, what this processing element does is it basically passes input M to the right, to P. It passes input N to the lower part. Q is equal to N. It does a multiply and accumulate on this, its accumulator. Basically, R becomes R plus M times N, okay? And we're going to use that to actually do a matrix multiplication. And again, as I said, I'm not going to go through this, but essentially, if you want to do a 3x3 matrix multiplication, you need to have 3x3 elements, replicate it. Each of them do exactly the same thing. And we basically feed the data elements of the different input matrices A and B this way. So A goes from left to right, and different rows of A go from left to right. So the first row of A goes from here. Second row of A goes from here. Third row of A goes from here. First row of B goes from here. Second row of B goes from here. Third row of B goes from here. And you basically see that A00 and B00 come right away. But B01 and A01, A10 are delayed by 1 cycle. So I shouldn't say first row. This is really the column. This is the first column of B. And this is the second column of B. And this is the third column of B. Okay. I said rows, but they should really be columns because you multiply their row by column, right? Essentially, that's what we're doing. But basically, you need to orchestrate the data so that you need to do the first computations first. And you need to ensure that the output of that computation, output of this processing elements arrives here before you input some input element over here. So this is a very simple example of matrix multiplication. Actually, it's relatively easy to do. And if you think about it, it makes sense because you need to delay the input, the third row of input, by 2 cycles over here. So you input 0, 0, because you should not do any calculation because the data item that you input from here did not arrive here yet, right? So basically, you need to figure out how long you need to delay the inputs into each element. So this element is the poor element, if you will. It needs to get the inputs from B and A after 4 cycles, if you will, because 2 cycle delay plus 2 cycle inside the array. Okay, you can think about this more, and it's very simple. And I think once you do the homework, you'll have fun with it. But this is a very simple example of 2-dimensional systolic array computation, actually. Okay, so this is from your reading, but you can see systolic arrays can be like this, depending on what you compute. Systolic arrays can be like this. Basically, there are different trade-offs which we're not going to get into. You can see 1-dimensional systolic array can be used, or 2-dimensionals can be used, but I'm not going to go into the trade-offs. You can read the paper for it. Okay, and you can see that the choice of a 1- or 2-dimensional scheme is very dependent on how cells and memories will be implemented, because it's all about overlapping and not overlapping of the latencies, for example. By the way, if I go back to here, this is the matrix multiplication, right? Here, we basically stored the matrix inside the processing elements. We didn't have to do that. There's another way of doing matrix multiplication where the result flows out. But I don't show it over here, and maybe you can start thinking about it. Here, the result doesn't flow out. Results get accumulated inside the processing element, and eventually you get C00 over here, C01 over here, C02 over here. And later you need to read the result out sometime in some way. But you can also implement a 2-dimensional systolic array that outputs the result as opposed to accumulating it inside an accumulator inside the processing element. Okay, think about that. Okay, there could be combinations also. In fact, this beautiful paper goes into a lot of interesting combinations. You can chain together systolic arrays to form even more powerful specialized systems. This particular systolic array, for example, is capable of producing on-the-fly least squares fit to all the data that has arrived up to any given moment. So it's basically what it's doing is it's really doing stream processing on real-time data. It's basically trying to find a least squares function that fits this data. It's a very statistical processing. It's doing some analysis on a series of data, basically. And you can see that data needs to be orchestrated nicely. Outputs need to be orchestrated. And you can see that it consists of two components. And I'm not going to go into them. You can read the paper. There's a systolic array that does orthogonal triangularization, and another systolic array that essentially solves that triangular linear system and outputs a result. And you can take a look. It's fun, actually, to connect these. And you can see how specialized these systolic arrays can potentially get. But specialization enables you efficiency as well. So that brings me to my next point, basically. The big advantage, well, there are two reasons why systolic arrays are very highly advantaged, because they're based on some principle, and they're also specialized. Basically, the principle is that it efficiently makes use of limited memory bandwidth. It doesn't need to go to memory for every single data item. It makes maximum use of one single data item by balancing computation to I/O bandwidth availability. And it's also specialized because it basically fits the computation to basically it has a particular computation in mind that it can do very, very efficiently, right? It's implemented to do that computation. But computation needs to fit the processing element organization and functions and the array organization as well. And if that is the case, then you get highly improved efficiencies, simple design, high concurrency, and high performance all at the same time. It's a very nice accelerator for that purpose. So basically, you can also do good. It's always good to do more with less memory bandwidth requirement in such an accelerator. So these two things combined together makes a very powerful accelerator, especially when you have a lot of data to deal with. You have a lot of data flowing into the systolic array and out of the systolic array, but systolic array itself doesn't need to go to the memory for every single data item, right? Because it really maximizes the operations that it does to every single data item. But the downside comes from the specialization, unfortunately, because essentially it's not generally applicable, right? Because computation needs to fit what we have seen, the processing element functions, as well as the array organization. And so you cannot apply everything to it clearly, right? And you cannot, it's not general purpose, as you can see. You cannot just run any program on it, as it's obvious, hopefully. So specialization is a big upside as well as a downside. Okay, so people later tried to improve programmability in systolic arrays. Basically, each programming element in systolic array was changed to store multiple weights. Weights could be selected on the fly, for example. This could answer some of your questions, for example. How do you decide which weight to use? So if you want to do adaptive filtering, for example, you may want to decide one weight set or another weight set. So basically, people added more programmability inside the systolic array and to ease the implementation of different operations and maybe make this systolic array more general. And taken further, this idea leads to maybe each processing element can have its own data and instruction memory as well, so that they can store intermediate results, partial results, constants, for example. That would be very useful. And instruction memory, so that you can do some general purpose processing as opposed to being limited to really fixed function processing, right? And this has enabled ideas like stream processing and pipeline parallelism. Basically, you stream data into a set of processing elements that are organized in some fashion. Each processing element has a small amount of memory. It still does maximum operations on the data you stream through it, but it uses its instruction memory and data memory to actually maximize its efficiency and programmability. So adding instruction memory and data memory doesn't really change the fundamental principle. It really makes it more programmable so that you can store partial and temporary results. And hopefully this memory is small. It maybe even registers to store constants, to store different types of weights so that you can choose between them. Adding instruction memory enables you to execute different types of instructions and become more general purpose, basically. So there's a question. Why is memory not a bottleneck when, for example, computing matrix multiplication? Don't you still need to load a lot of individual data? Yes, absolutely. So memory is always a bottleneck, and systolic arrays reduces that bottleneck, but you still need to provide the input data to the systolic arrays. No question about that, yes. And matrix multiplication may not be the best example also. There are better fits for systolic arrays such that you really don't need to, you really do more with an individual data element, basically. In matrix multiplication, you actually don't do a whole lot with an individual data element. So that's a very good observation. Okay, so basically this idea of systolic arrays has actually led to a lot of bigger idea about more general purpose ideas like stream processing and pipeline parallelism, and more generally state execution as well. So what is state execution? Let me talk about pipeline parallelism very quickly. So this is one way of parallelizing your code. And in fact, parallelizing an inner loop, for example. So this is an inner loop. You have A, B, C. Normally, you may not be able to parallelize it, but because you have some dependencies between B and A, and C and B, for example. So there's some data flow that goes from A to B and B to C, for example. And normally, if you execute in a single processor, that looks like this, clearly sequential. But you can split each iteration into 3 pipeline stages, A, B, C, and execute. Iteration I, for example, comprises of AI, BI, CI. And instead of sequentially executing them on a single processor, you basically pipeline the iterations, pipeline each piece of the iteration across different processors, P0, P1, P2. P0 executes A part of each iteration. P1 executes B part of each iteration. P2 executes C part of each iteration. And you may have nice connections between them. You may actually specialize P0 to do A very well, specialize P1 to do B very well, specialize P2 to do C very well. Or you may be a multi-core machine, such that you have nice connections between the cores. You may be general purpose. Each stage essentially executes on one processing element. And you basically do A's here, B's here, C's here. That way you can essentially parallelize this loop iteration internally across different processing elements. So you get basically higher performance. You may not be able to parallelize different iterations of the loop because there may be loop carry dependencies, right? But this still gives you significant performance. And this is the idea of pipeline parallelism, basically, which is used in some parallel programming paradigms. And this fits very nicely to systolic computation as well, especially when A, B, and C are common computation patterns. And you can actually specialize your accelerator to do A, B, and C. And there are multiple other reasons to potentially do this. All of the A's may be operating on similar data, for example. They may have very good data locality, so that you want to keep that data inside this processor. B's may be operating on similar data, such that you want to keep data over there. You basically maximize the locality over here as well. Again, I'm not going to go into that aspect right now, but this is a programming paradigm that has been inspired by systolic computation and stream processing. And this also fits nicely with the systolic array principles. If you're interested, you can actually read this paper that we had written in ISCA 2010. But I've already said this, but basically we divide the loop iterations into code segments called stages. And each loop has different parts, let's say 3 stages in this particular case. Threads execute stages on different cores. This is a general purpose programming model, but each core may be a processing element, as you can see. And you can see that each core has a queue associated with it, and they can communicate with each other through these queues. Okay, I'm not going to go through this anymore. You can look at it. But essentially, some programs can be written this way also. So this is file compression, for example, that is done in a streaming or pipeline parallel manner. And you can do all of this in software. You can all do all of this with hardware support as well. But basically, you get an input file, and you keep streaming through different parts of the input file, and maybe different files as well. It depends on what you're doing, basically. You first allocate buffers at stage 1, and then there's some buffer you put, and then you read the input from there, and then you do the compression. You can actually have multiple stages for compression. Writing the output can also have multiple stages, and then you deallocate the buffers. Basically, you minimize the memory accesses by having specialized queues here, for example. If you do this in software, of course, you go through memory. But if you do this in hardware in an accelerated fashion, the way we are talking about systolic arrays, you don't need to go through memory each time you do this. Basically, with each input element, you don't need to go through memory in any of these stages until you output it. Okay, so this is one example that you may want to think about. And this is the example of pipeline parallelism. Okay, I'm going to, and these stages can be executed in different processing elements, as we discussed, that are specialized for different purposes. Okay, let me cover the disadvantages and advantages again with systolic arrays. Basically, we make multiple use of each data item, like in the previous example, hopefully. And this leads to a reduced need for fetching and refetching, better use of memory bandwidth, high concurrency as well at the same time, and also a regular design, both data and control flow, which enables specialization. But of course, it's not good at exploiting irregular parallelism, as we discussed. As a result, it's relatively special purpose. So you need software programmer support to be a much more general purpose model. And that's not easy to add. But more recently, people are adding that support. And we will see that with Google TPU. But before we go into Google TPU, the first systolic arrays were actually implemented at Carnegie Mellon University, where I used to teach, where H.T. Kung used to teach also. He did some of these seminal works on systolic arrays while he was there. Basically, they wanted to accelerate vision and robotics tasks at the time. They can read the papers that they have written. They had a linear array of 10 cells. Each cell was a 10 megaflop programmable processor. We will see the TPUs. That's going to be 90 teraflops today, but we're talking about 1980s over here. And this was an accelerator attached to a general purpose host machine, just like what a TPU is. And they had a high-level language and optimizing compiler to program the systolic array. And I think TPUs actually have some of these and going to have some of these also increasingly. So the initial vision of the systolic array that looks like this is kind of, I don't want to call it reinvented, but resurfacing right now with tensor processing units, which act as systolic array-based accelerators for machine learning tasks. And you can see that this is a simple linear array. They called this the warp processor array at the time. And if you look at a single warp cell, it's not like the very simple systolic array that we have seen, but it has other things. For example, it has a very simple memory to store constants, to store different weights, for example. As a result, it has an address generation unit. It has some simple registers, address registers. You can see the multiply and accumulate units over here. And you can see they basically added simple memories here so that they can, local memories, so that they can actually do more general purpose tasks. But you can see that the input queues are X and Y, which are actually visible over here, X and Y. And some of them are bidirectional, as you can see. X is unidirectional over here, but Y is bidirectional, as you can see. Y is output over here. So basically, there's interesting design trade-offs that you need to make in the design of a systolic array. And this is a very good example that I would recommend people to look at if they're interested. So let's go back to the modern systolic arrays. These are TPUs. Essentially, you can see a TPU does matrix multiplication, and it's designed to do matrix multiplication. And you can see that in this paper, it's described in more detail. Basically, they have a systolic data flow into the matrix multiply unit. And they basically say software has the illusion that each 256 byte input is read at once, and they instantly update one location of each of 256 accumulator ramps. Basically, they actually have, I mean, it depends on how you program it, but you can actually accumulate the results inside the systolic array as well. But you can see this paragraph from the Google TPU paper. Figure 4 shows that data flows in from the left, and the weights are loaded from the top. I don't know if this is figure 4, but yeah, this is a figure 4. Weights are loaded from the top. They don't show it over here. But a given 256 element multiply accumulate operation moves through the matrix as a diagonal wavefront. You can think about that. The weights are preloaded, as we have seen earlier, and take effect with the advancing wave alongside the first data of a new block. Control and data are pipelined to give the illusion that the 256 inputs are read at once, and that they instantly update one location of each of 256 accumulators. So they try to hide the complexity from the program as much as possible. As they say, from a correctness perspective, software is unaware of the systolic nature of the matrix unit, but for performance, it does worry about the latency of the unit. This means that if you really want to optimize for the performance, you need to know what's going on in the systolic hardware over here. Okay, so this is the example that you're going to do in your homework, which is essentially the same, except it may be a different way of actually implementing the matrix multiplication. Okay, so if you look at the TPU, this is the broader picture of the system. There's a matrix multiply unit over here, as you can see, and you can fetch the weights over here from the top, and the input data over here, and the accumulators are over here. And basically, the data gets recirculated to the memory. So there's a lot of system level infrastructure that you actually need to build to make it work with a real software stack. And that's what I was talking about, basically. If you really want to make this work in a general purpose system, the slide I showed you earlier, you really need to think about the software stack and the system controls to enable this. And that's what this Google paper is talking about that was written in 2017. Okay, later, Google actually developed other TPUs, which are based on the same fundamental principle, but they basically figured out that you need more parallelism to do the training. So they have 4 TPU chips as opposed to 1. They have high bandwidth memory so that they can do memory access much faster and much higher bandwidth. They have floating point operations to do the training better, as opposed to some proprietary format that they had. Now they can do 45 teraflops per chip, and this is designed for training and inference versus only inference in the prior TPU chip that I showed you over here. Now, actually, they have released TPU3. They use this internally in their system, so they don't actually release it outside, but internally, they need to do a lot of training in their data centers. So that's why they found that it was important for them to design these accelerators. But if you look at a TPU3, which was more recently released, now the memory becomes bigger because they need to deal with larger and larger data sets, and they need higher bandwidth. So per chip, they have even high bandwidth memory. They have more matrix units per chip as opposed to 2. Matrix unit is essentially the systolic part. That's the systolic matrix multiplication unit. And as you can see, they can do 90 teraflops per chip as opposed to 45 teraops. This should be teraflops, actually. We will correct that. It should be teraflops in TPU2 also. Okay, so hopefully this motivates you to understand systolic arrays even more. And there's a reason why systolic arrays is used. If you read that paper, you will see that they basically suggest that this is much more efficient than other types of computations they thought about or tried. Okay, there's another engine, as you know, that's built for machine learning, Cerebrus' wafer scale engine. As far as we know, this doesn't necessarily use systolic arrays. It uses SIMD, which we're going to talk about in the next lecture. But I will show you this picture that I showed you earlier. You can see that it's a wafer scale. It's a full wafer, 1.2 trillion transistors. But they actually released a recent one. This has now 2.6 trillion transistors, and it's still 46,000 millimeters square. It has 850,000 cores. I wanted to show you this one because this was released in 2019, and this was released in 2021. So they improved the process, and as a result, they were able to get more than 2x times the transistors and more than 2x times the cores. And this is, again, showing the importance of how much computation need and memory need is there for machine learning going into the future. And we're going to talk about the basic principles, SIMD principles, that this Cerebrus engine is probably built on in the next lecture.